Well, thank you all very much for coming to the April North Houston Space Society meeting. Yes, let's go. We're here, yay! And I'll let them see all. That might be better. Okay, cool. So let me tell you what the plan is for today. I thought we'd start off with some opening remarks, and then we'll have Greg come and let us know the highlights of all the things that have been happening in the space world since our last meeting. And then we'll have Gary come and talk about big ship propulsion and how we're actually going to make it to Mars. So I'm really excited about that. I guess first off, and hold on just a second, I need to just click there. First off, that was the plan. How many of y'all have Netflix? How many of y'all watched Apollo 10.5 that came out the Friday before last?
Haven't seen it yet.
Haven't. It's really good. I really liked it. It starts off with a fantastical premise of NASA made a math error and made and made the lunar module just slightly too small, and he needed a 10.5 boy to go and take it to the moon. And then it starts to show you about the 1960s and kind of what was going on in Houston. I mean, we built the Astrodome, we built Astroworld. Everybody thought space was just around the corner. It was really a magical, fantastic time. But I have another connection with Apollo 10.5. Many of y'all know about my Countdown to the Moon project. Mike Blizzard, I had actually interviewed him for my project 2 years ago. And there's a few little snippets about that project, but he's the producer and director. And about Countdown to the Moon, if you're not familiar with it, is my personal oral history project of interviewing a person a day to the end of 2024 to kind of capture this moment in time before the age of space exploration truly takes off. And I've been dying to get that takeoff part in here. So, okay. But if you think about the 1960s dream, you know, back in 1960s, lots of things came out. We had Space Odyssey 2001 with big orbital space stations. Star Trek came out. I guess we had Buck Rogers and the Jetsons and all sorts of other things that I hear about, but didn't get to experience. But about the space station thing, if you look at what we have now, we have the International Space Station that's actually been continuously inhabited for 22 years and currently has 11 people on board. And I think it's going to have 4 more on board before the Axiom crew comes down. So that might be 15 people, which would be a kind of a record. And we have China's space station, but in the near future, Axiom is also going to be making a station. We have Orbital Reef, and we have many, many more space stations that are in our future. So it's really an exciting time. And just thinking about back to the 1960s, you can't really make it up there, but this right here is the first moon flight club from Pan Am. Pan Am in the 1960s thought that it was just a matter of time before we'd actually go to the moon, and they were signing people up ahead of time. And thousands of people were in line to make that trip to the moon. It didn't quite work out that way, but if you do look at what's been happening now, you know, we had the Inspiration 4 mission last year. We have, you know, Blue Origin, Virgin Galactic, all taking people to space. So you can actually see sort of that theme that we're at between the dreams of space becoming reality. It's really an exciting time. And I would even argue that when it comes to space, the 2020s will be what the 1970s should have been. Now, yeah. So it's time to participate. And how can you participate? Well, you're already doing it. You're here to learn about it, here to talk about it, encourage other people to go into space-related fields. And one thing is about translating that vision of space into everyday language that non-space people can actually relate to, which is a challenge, but one that I think you're up to. You can also invest in space, but those are just some of the things that you can do, and I'm sure we can think of thousands of other things to do. I hear some people do that. Awesome. Well, I think with that, Greg, I'll go ahead and pass it off to you, and you could tell us the details about why we should be excited.
Okay.
I'll oh, yep, here you go. Yeah, on top of it.
This is art on the moon.
Yes. That's interesting. Okay, I'll see.
But it looks like inside one of the ice deposits at the South Pole.
Yeah. With a lot of bright light. Yeah.
Okay.
Okay, so we all set?
We are all set.
Okay, so space news for the previous months as of April 9th. Okay. Clicker's not working here.
Oh, I'll take care of you.
You'll see the same stuff in the later slides anyways. So. Okay, well, we'll start right off with the James Webb Space Telescope. We've been following it all along, of course, and the big thing is that actually it's really coming close to being ready. They complete the alignment of the mirrors, which is a big thing. It's a little hard to see on this, but in the lower right corner there, that was an image of a star with all the mirrors converged. Remember, this thing had all these different mirrors. Each one had to separately be aligned to be, pointing to exactly the same place. When they started, they would have had, 16 different images of stars, and now they're down to one. Apparently, those artifacts, the rays shooting out, that follows apparently from the hexagonal mirrors, or maybe a lot of other geometries as well. But I guess with software, they can remove those. They didn't bother for this particular picture, but they can do that. So anyway, those images, what they're saying is those are now calibrated as finely as the laws of physics would actually allow. In other words, it's in perfect condition. Now, it isn't completely ready yet. There's still 3 more instruments. They have various instruments up there of different wavelengths and so on. They're still working that. The other thing is they can't really start it completely because the thing hasn't cooled down enough yet. It's already been up there all these months, but it still cools down at a very slow rate because it's just radiative heat transfer to get rid of the heat on there. And they're getting pretty close to the point where now they'll be ready to start up the additional helium cooling that they have a cycle for that. And so they're very close. They'll end up going down to 7 degrees Kelvin, which is 7 degrees Celsius above absolute zero. And they're down at like 20 or something now, 24 maybe. They expect to be ready by June, which is pretty much the original timetable. So things are looking really good. Most people, including me, are pretty surprised that this actually worked. I mean, it was so incredibly complicated. They had to squeeze all this stuff into the relatively small fairing and unfold it like origami, and they managed to make it work. So that's coming along nicely. The picture in the background there, just a reminder how it's set up. In that you draw a line from the sun through the Earth, and the Lagrange point out here, L2. They're orbiting around that, and what's called a halo orbit is sitting out there. The part facing the sun it has a lot of layers of shielding to protect, to basically keep it cold, so that the observatory points outwards, away from the sun, so that it doesn't, because it is mainly focusing on infrared. Okay, next big thing from a NASA standpoint is the Space Launch System. They rolled the thing out really for the first time. It has this, this huge tractor actually left over from the space shuttle days, or even Apollo days, maybe. They put new engines on it and so on, but they rolled the thing out, they got it all set up, doing what's called a wet dress rehearsal. And they call it wet because of loading it up with actual fuels. To the point, the idea is to take a test all the way down to about 10 seconds before you would actually launch. So you go through all the steps you would do and then unload it, and make sure you can unload safely. So that got started. It got delayed quite a bit. They were having a variety of problems. One thing that's kind of interesting is they're on a particular launch pad, which is 39B at Kennedy Space Center, which is right adjacent to 39A, which is where this mission that's going to the space station, the Axiom's mission is. And so they're kind of competing with each other. There's some common utilities, things like nitrogen lines and that sort of stuff. they can only service one of these at a time. So it takes a certain amount of scheduling to even manage this stuff. So NASA said, okay, SLS, they get priority. So they got priority, so they were all set to go, but they ran into all kinds of problems, not necessarily anything that's considered horrible, but just the kinds of things that testing is supposed to uncover. And so they ended up delaying it. They had problems of all various types. There's some vent valves. They have some fans that are basically keeping positive pressure in areas where they want to keep explosive mixtures out, things that might explode otherwise. They had problems with that. They had problems with the liquid oxygen getting too warm in places. And so they say you get kind of a geyser effect. It starts kind of boiling up and that gets unsafe. So they had all kinds of problems like that. They had to halt. They said, okay, instead, do the Axiom space mission instead, which I'll talk about on the next slide. So anyway, it's halted.
It's not about completely draining everything out wet out of the SLS.
Well, they put everything in it and then they have to drain it all back out. And,
before they can.
Yeah. Oh, they don't leave it in there. No, I mean, it has to, yeah, it definitely has to all go out. So they did that.
Yeah, before they can do the SpaceX launch next
Yeah.
summer.
Well, probably. I don't know if they really, but I think they do, yeah. So anyway, they've halted the test. Now it's currently scheduled apparently for Thursday, I believe, which is after the Axiom launch. Okay, so that's that one. This is the one that was on the adjacent pad. This is the mission. This is the first all private, all commercial mission flight to the ISS. There have been lots of missions to the space station that involved, movie stars and everything else, but they always were flown there by a cosmonaut, actual professional astronaut. This is the first one where actually everybody was private. There were 4 people that went, 3 of them paid, including the pilot. The pilot, they paid $55 million a seat. The guy who was the official pilot was one of those paying customers. That was kind of interesting. But those guys actually all had pretty serious experience. The mission leader, it was an astronaut for some years ago. And anyway, so they pay their money, they get to go on this. In a way, the whole thing is kind of a demonstration of gearing up for private space access. And this is just kind of a step along the way. And that's really, I think, the best way to look at it. It's a 10-day mission. 8 of those are spent on the space station. It launched April 8th, but yesterday, I guess. It was going up on a Falcon 9 rocket and with the Dragon spacecraft. So the same kind of thing they've been taking the astronauts up with. One thing I found kind of interesting is the mission control for this is actually out of the Axiom headquarters, is not out of NASA. Now, when I say mission control, I'm talking about once they get there. I think SpaceX actually controls everything up to the point, up through docking. But after that, they turn it over. So this mission control, and there's a little bit of a picture here. I'll show a larger one in the next slide. That particular control center is officially designated as a payload operations site. So they've already used it at least one other time. They run a variety of missions on the space station, and then they control them separately from the routine operations of maintaining orbit and attitude and all that. So I found that kind of interesting that they're gearing up. This is a little bit bigger. This is one of their PR kind of things, but probably the lowest picture here gives the best idea. You can kind of see it's like a typical control center where you got lots of full-size screens, and you got people in the back in there doing the actual individual jobs and so on. So, and then there's a little bit closer view up here on the right.
Physically, like down towards Clear Lake,
I assume so. I think that's where their headquarters is, but I'm not actually sure. It's somewhere in Houston, or Houston area.
Okay.
Yeah, I mean yeah. In fact, I was wondering, are they? Do you know exactly where? I mean, is it like at Ellington Air Force Base?
Buildings. They have even a couple of buildings inside of NASA site. So.
Oh, even that inside. Oh, okay. Yeah. So anyway, it's kind of interesting. This is just another sign of things are shifting. More and more private activity getting going into space. Now, the next topic is the space station operations. With the Ukraine war, most cooperation and with the Russians is pretty much stopped. This is still the one place that has not really been seriously affected, is the space station. You could actually say there really hasn't been a significant change. There's been a lot of bluster. The head of Roscosmos, the Russian space agency, that guy's kind of a windbag, and he likes to just shoot his mouth off. But the reality is, on a working basis, not much has really changed, surprisingly, considering everything else that's gone on. There was a launch of a new crew from Russia. on a Soyuz capsule went up, and that included one American. And then returning, they did a return craft on March 30th. This Mark Van de Heye, he actually set a record for the U.S. anyway, being in space. The longest person in space is still Russian at this point. So the background pictures here, that's them returning to Earth. In the Soyuz capsule, they dropped down in Kazakhstan or somewhere.
So Greg, there was some confusion that was occasioned when the 3 cosmonauts got aboard the space station and they came in wearing yellow suits, pressure suits with blue.
So everybody interpreted that as supporting Ukraine. And
what they said was all 3 of the astronauts went to like Moscow State University or something, and those are the school colors.
Yeah.
It's like, okay. And
it really is mostly yellow with a little bit of blue trim. You look, there isn't that much of actual blue on there, whereas the Ukrainian flag is really split 50-50, yellow and blue. They interviewed, Mark Van de Heye. He said that, he's probably not going to really say anything to endanger those guys, but what he's saying is that they were kind of blindsided. And you figure in Russia, they pretty much are cut off access to the outside world news. Their people don't really know what's going on there necessarily. And they might have been, he said they were just completely blindsided. They have no idea. But it's, on the other hand, it was sort of weird. Oh yeah, we had all this yellow material just sitting around. So, who knows? There's one of those things where maybe in 20 years, somebody's going to write a memoir and we'll find out the truth. Or maybe they'll lie in their memoir. You just don't know. Okay, the next topic on this is also somewhat related to the Ukrainian war, and that's OneWeb, which is the biggest competitor so far to Starlink, which is a constellation providing internet service, space-based internet service. All of their previous launches, which were, how many was that? 428 satellites that have gone up already. They all went up on Russian Soyuz rockets, every one so far. And they had 6 more launches to go, 6 or maybe 7, this in that range, say 6 for another 220 or so satellites. And with everything that's gone on, who quit first is kind of hard to say, but they basically gave up. The Russians said, oh, you had to swear that there won't be anything military on there, and you have to throw the UK government out of the project, which is a co-owner of it. So that wasn't going to happen. So anyway, they decided they would have to go ahead and go somewhere else. Now, we talked about this last month, that there isn't really all that much launch capacity around, especially medium to heavy kind of launcher. It's just not there. And so they pretty quickly came to the conclusion they had to go to SpaceX, which is a little bit awkward for them because they're competing with SpaceX in the case of the Starlink internet service. But on the other hand, they need the launch service. So they took the pragmatic approach and said, okay, fine, we don't have much choice. Let's go. And SpaceX was okay with that. So they're doing it. So the details of the agreement are undisclosed. They haven't really said, well, is this on a Falcon 9 or is it on a heavier, the heavy? We don't know yet. And we don't know the prices or any of that. And we don't even know if they're going to do all the launches on there. What a lot of people had speculated was that they'd already paid up front to the European Space Agency, who was acting as the sales agent for Russia in this case. They're still trying to squeeze some of that out of Europe. So that would maybe, if they can wait, maybe the last couple flights might be on an Ariane 6, which is the next rocket coming along. So we'll see. We don't really know. But bottom line is, they were pragmatic. They went with SpaceX because that's really about the only game in town at this point. So we'll have to see what happens on that. The other question about that is still unresolved is they already had their 36 satellites sitting there ready to go from the Russian launch site. Russia basically just took over control of those. There's no way to ship them back out anyway. I mean, nobody was going to be allowing much transport going on there. So no one really knows what's going to happen, but I think basically they have to say, okay, we're giving up on these satellites. It's not that big a deal for them. They make 2 a day. So to replace 36 satellites takes them 18 days. I mean, obviously there's cost involved, but what the CEO said was that was really one of the least of their concerns. I mean, a much bigger one is just availability of rockets and doing the conversions, because they had a system all set up to disperse the satellites, and that won't necessarily fit as is in the Falcon 9. So they have work to do, and losing a few satellites was not really the top of their list. So that was kind of interesting. Okay, now as long as we're talking about internet service, this one the Project Kuiper from Amazon, we hadn't been hearing a whole lot about them lately, but it's huge. You know, it's just like Starlink in the sense it involves thousands of satellites. 3,236 is the you know, the number of satellites they're talking about putting up. And they'd always talked about it as being like a $10 billion kind of a project. And it had been pretty quiet, but I guess they started to get worried too that, oh my gosh, where are we going to find all these rockets to get, you know, all of our satellites up there? Originally, of course, they probably hoped that, you know, Blue Origin would supply that lift capacity. And that would have made sense because they're all owned by Jeff Bezos, Amazon and Blue Origin, but they're just not far enough along. So what they did was they actually put out contracts, the largest set of contracts ever in the launch business, for up to 83 launches. 60 some, you know, are committed to, and then there's some options on 15 more. And they split the business among everybody but SpaceX, essentially. So anybody that didn't have SpaceX in their name, they get essentially they're getting a lifeline through them because these guys are all getting killed by competition from SpaceX. So first of all, United Launch Alliance, they're going to get 38 on their Vulcan rocket. Now, of course, that rocket doesn't actually exist yet, or at least it's not, you know, not usable. Those would probably each launch about 45 satellites. Blue Origin will get some. They're going to have to come later because the rocket doesn't exist yet. With an option for 15 more. And Ariane Space, that's the next European rocket to come along. That one, they're going to do some launches as well. Of course, that rocket doesn't exist yet. So they're putting all this money out supporting 3 vendors that don't actually have rockets that work yet. But on the other hand, Ariane 6 is pretty close. They're using the same engines as the last generation. That's probably going to come this year.
What about Cygnus?
What?
The guys launch out of Wallops. Cygnus.
Astra.
The OSS.
Rocket Lab. You're talking about Rocket Lab, or they're not even launching there yet.
Yeah.
Well, nobody else, they're not big enough.
The guys said, Minotaur rocket, but yeah, that wouldn't be big enough.
Yeah, you need big rockets.
All of those at once, they might have to.
Oh, you'd have to do one at a time. I mean,
This part's pretty expensive, and it uses Russian inputs, so it uses.
Yeah.
I don't think you're getting one of those.
very few details have been published about these particular satellites, but partially based on these contracts, people are assuming these are about twice as heavy as the satellites that are being used by SpaceX for Starlink. And you're talking about, you know, you could probably only make 1 or 2 of those in something like a Rocket Lab launcher at this point.
They launched the first time last year.
What?
ULA's Vulcan, they launched it last year for the first time.
Oh, they did. Oh, okay. I thought the thing. Oh, okay. But there's 2 different versions of it. That's the problem. The old Vulcans are the ones based on the Russian engine, and they only have a couple of those left.
No, and the new one that they carried ESA's cargo.
No, that's you're thinking of the Cygnus.
No, it was ULA because I saw them in the conference and they were talking about it and like I remember that they launched it.
Well, some goes in the because the new one relies on the BE-4 engine that comes from Blue Origin, and that has not flown yet. So, I mean, I think they're reusing their name. I think they're using the same name that they've had before, but all the ones coming up are depending on the Blue Origin engine, which doesn't exist yet. Well, I think they've delivered a few prototypes and they've been testing them, but it hasn't flown yet. So they couldn't have actually launched something. I think, yeah, you're talking about earlier, they've been reusing the name, I think. So anyway, so basically, you know, Russia's out of the picture and then SpaceX is out of the picture, and that leaves these. So all these guys are kind of struggling. You know, all of them, it's interesting. You know, you think about what's this going to cost? Well, yeah, they're not saying the amount. You know, the original project was assumed to be $10 billion, but you start thinking about what does it cost to do a launch? Even if you're using a Falcon 9, they've raised their prices. They're like it's $67 or $68 million for a launch now. And so you say, well, okay, traditionally everybody thinks that all these other vendors that don't have reusable rockets, they're going to cost 2 to 3 times as much. It's going to be at least the $70 million a launch. And even the 68 launches they're committing to, that'd be like $4.7 billion right there. So this is really a big shot in the arm for all the existing players. And, you know, by the standards of SpaceX anyway, the Ariane 6 is obsolete because it has no reusable part whatsoever. So that is never going to be cost effective, and yet it's not even out yet. The United Launch Alliance one is kind of interesting because they're so far up to this point. They've been saying they could make part of it reusable. They were going to have a collar to hold just the engines, and they would drop the engines and catch them by internet from a helicopter. But they didn't actually do anything toward that. Now they're saying, okay, they're probably going to do that. They probably have to just to keep the cost down. So that one's going to be partly reusable. Blue Origin would be reusable, but it's just not far enough along yet. It's the farthest from completion at this point.
So Blue Origin's having problems with that engine. Is there any information, or are they playing it very close with us like they traditionally did?
Well, ULA keeps saying they're okay. They think things are coming along. So they're playing close to the best. They're saying it's coming along. But then again, they said that 2 years ago. So I'm sure they're coming along. We just, when it's ready, we don't know.
I think it has to happen because they need to replace Atlas V. We're not getting any more Russian engines.
Yeah.
And even if we could, I think Congress has already said that, yeah.
Oh, yeah.
We're not using that anymore. So
they'll make it work. It's just a question of how long. And yeah, and the thing is, so that all it says is that 2/3 of these really are depending on Blue Origin because the Vulcan needs the Blue Engine rocket, and of course the Blue Origin needs the same rockets, or engines. I'm sorry, so that they're all needed. But anyway, it's the largest deal ever, and they originally had 9. I'm sorry, they had 9 Atlas V launches already lined up. So the initial satellites are going to go up. They can do those because that's just on the Atlas rockets that are sitting around. Those are the old ones using Russian engines. That's not a problem because they have them already. But you think about what this means for the rest of the business. This soaks up all the capacity in the medium to heavy range. If anybody wants to launch anything, they're going to have to go to SpaceX. There's just really no other alternative. Now, there are a couple new ones coming along. Rocket Lab will have a bigger rocket at some point here, the Neutron. And Relativity, that's the other one that most people highlight is coming along. They'll have something, but you're probably talking a couple of years at least. So for the next few years, SpaceX can charge whatever they want. And in fact, they probably are in the next slide. One last point on this is that they have a pressure of time here. They have to get licensed by the FCC to be able to launch these satellites. Their requirement back when they got approval was half of the satellites had to be in orbit by 2026. And then the other half by 2029. And so the clock is ticking. And so they're really feeling the pressure. So they're now moving, and that's why they're signing up these contracts, because they realize even if they can produce the satellites, they got to get them up there. And without having the backstop of having the Russians available, it's just one less vendor.
Can't they appeal to the FCC for there was this thing called COVID. Then there's this
Sure.
thing called supply chain snarl.
Yeah,
There's
they
another thing called almost World War III in Europe.
Oh yeah, and they will. But still, I think they have to make a good faith effort. Probably they won't get as many up as they're supposed to, but no doubt they'll get a pass for having made a good try.
you get approval to take up some chunk of benefit. The FCC has the use it or lose it policy. So if they don't use it, then the FCC is going to license it out, probably to their competitors, because same satellite or same type of internet service is going to have to operate the same microwave bands.
Yeah, they're all using pretty much the same bands. So yeah, and that's why the FCC is involved. Is really allocation of spectrum. It's not so much satellites bumping into each other. That's not really the FCC's main concern. It's really spectrum allocation. So
the problem is it will all be safer because then that bandwidth will go to the FAA, and so we won't have airplanes falling out of the sky because of the interference.
Well, they've already figured out that it's going to be okay, so that they already have the permission. It's just a matter of now can they actually do it.
I don't think anybody's there to fall out of the sky just because somebody's translating. Otherwise, they would have already fallen out of the sky.
Yeah. Okay. So we were talking about pricing, and it's interesting. SpaceX has been the price leader. Even their prices are going up. And now maybe some of that's because right now they can get away with it, but part of it is they're saying everything is costing them more too. So they've raised their prices typically about 8% across the board for launches, and also for Starlink internet service. The monthly charge is going up. The terminal charge is going up. The thing you have to is your antenna basically. And that was going up 20%. But then again, the actual cost of that was probably about $1,300 in the first place. So they were subsidizing those so heavily. I guess they're sort of thinking, okay, maybe they were hoping to get the costs down. They didn't get them down as much as they wanted. They were going to charge more. So that's it. You know, you compare that to the consumer price index, that's going up almost 8% a year. So they can pretty easily raise their prices. But it's kind of interesting. That's the first time in a while that prices have gone up in space. Mostly they've been on a downward trend for quite a while. Okay, one last thing is kind of a little different topic. And that's that you're probably wondering, where is that? That's in Norway. There's a company called KSAT, Kongsberg Satellite Services. They just decided pretty much on their own, well, with some funding from the European Space Agency, I think, they're going to set up a network of antennas on Earth for communicating with people that are on the moon. Well, not people necessarily, but even just devices, launches, and so on. Boy, I can't even see this. Oh, okay. So the point is, you know, if you're going to do that, that says you have to have that site spread around the Earth, at least 3 different longitudes, so that no matter where you are as the Earth is spinning, you can still be in contact with things on the moon. They're going to basically put in, you know, a big network. They already have it. They do this now for low Earth orbit and up through geosynchronous orbit now. They're a typical vendor that supplies this. They already have all these kind of antennas. But what they're saying is they need bigger antennas for reaching the moon. So they're going to focus on putting in more new ones. And as an example, Intuitive Machines, they're going to have a lunar lander in 2023 or 2024. You know, that's a customer of theirs. So there are people, they're planning on doing their communications back to Earth through these people's networks. So they've lined up already a set of customers for this. But the reason I bring this up is more just another example of the world is kind of gearing up. You know, kind of gearing up for more activities in space, and it's really interesting and spreading out. You know, most of the activities so far has pretty much been, I mean, outside of a few exploration things, it's mostly been satellites around Earth, and now they're starting to expand a little bit more, thinking more about regular communications. You know, we talked about NASA's Deep Space Network before. You know, there's a few big antennas for communicating all the way to Voyager, you know, and those kind of things. But this is more for much larger scale use. You know, the industry is gearing up for it. Miscellany, Blue Origin launched another 6 people in this case, you know, in their 10-minute ride. Another miscellaneous one, SpaceX, when they did their recent news conference back in February, they alluded to the fact that they have 2 versions of their engines, the Raptor engine, which they're using for Starship. Version 1, you know, was working fine. Version 2, they said they were going to be using it, but then they dropped this bombshell in the middle of their press conference saying, oh, but we're having trouble with the engines melting, at least at full thrust. They really, you know, and you saw some of the pictures. If you saw some of the rocket tests, when you saw green smoke, you know, green exhaust coming out, that's vaporized copper, which is from the components. There were, you know, some of the copper components inside the engines. And that was just mentioned as kind of an aside. Oh, we've got to fix this melting engine problem. But so there was some question as, well, what are they going to do for future testing, including the very next launch? Well, it turns out they're still going with the Raptor version 2 because it is a lot better engine. It's simpler, cheaper to build, it's lighter weight, more powerful. And a big thing for them is it's much faster to turn it around. I don't know why, but apparently you can turn them around pretty quickly. So since their goal is to have very rapid reuse of everything, that mattered. And so for all that, they're committing to it. And my guess is they probably just don't run on full throttle. I mean, apparently they test just fine up to some percentage of their maximum thrust. And so you're doing it. But we'll be able to tell if you see any of these, you know, you see one of these launches and you see a lot of green, you know they're still having trouble. So we're at that point where I asked, how many launches have there been since the last meeting? Roughly a month. And as usual, of course, that doesn't account things like you know, the Blue Origin launches for 10 minutes. They don't make it to orbit or beyond. They don't count. This is a serious one. So how many people think there were more than 11 launches? How about less than 10? Okay, well, turns out the answer actually was pretty low this month. It was 8. Oh, got our usual problem here. Actually, we only had 8, and we've already talked about a few of them. That's the lowest count we've had in quite a while. Yeah, Well, there was kind of a drop off for a while back when COVID was really raging, and now I think there's maybe a certain amount of distraction because of the Ukraine war, but some of this is just variation of normal stuff, I think. I mean, there's still 2 launches from Russia, both of them, involving one of them involving the space station anyway. China had launched a couple like they always do. There's another one of those SpaceX launches on a lot of small satellites where the missions are called transporter. They're up to number 4 now. It's basically rideshare missions where you have lots and lots of small satellites. Or in this case, it was one pretty good sized German satellite and a whole bunch, Snow White and the 7 Dwarfs kind of, or 39 Dwarfs in this case, a bunch of small ones. I think that's pretty much it. So,
Can you say anything about the swarm space balls up there?
oh, Space Beast. Yeah, we had talked about this, I don't know, maybe sometime last year. These are the satellites that are the size, they're a quarter of a CubeSat. That is, they're the size of a cheese sandwich. Somebody at that company likes cheese sandwiches because they specifically said a ham and cheese sandwich or something. They're the smallest satellites ever. What they're for is basically tiny text messages, like you do on your phone, except anywhere in the world. A limited number, but it's really oriented more toward people getting automated data. If people are collecting information, on location of a whale, or temperatures in some part of Antarctica, or maybe temperatures around a forest fire somewhere, it's that kind of thing. And it's like $5 a month. I mean, it's actually really cheap. So anyway, they launched these satellites. I forget how many. They might have a couple hundred or 100 satellites anyway, but they're also tiny. You don't even notice them. So those have to be the smallest satellites up there. So they put a bunch of those up. Those have been going up periodically. But that's the one that got bought by SpaceX. It's about the only company that SpaceX has bought, except for some machine shop, many years ago. They were impressed enough with this technology that they went for it because they're so cheap. That's the thing, is even the hardware on the ground, it's, you buy a kit for $500 or something, and you can set it up. So that was kind of interesting. That's Astra. Astra, they're one of these small launch providers. They can't get very much up there, but when they, things like that, it works just fine. Okay, I think that pretty much is it. Any further discussion or questions? All right, now we get to our featured speaker, Dr. Gary Johnson. Sort of a Renaissance man, as far as I can tell. I mean, he's an aerospace engineer, but also he knows how to kill cactus and build equipment to do that. So it's a little of everything. He's been involved in aerospace. He's been an aerospace engineer basically all his life, but he also got involved in automotive stuff, all alternative fuels. So in this case, like that little VW Beetle there, that actually was run on alternative fuels, what I picked up somewhere. And the same goes for that little plane that's down there with him in front of it. He does have patents on ramjet rocket motors and also tools for controlling prickly pear cactus. So if you need either one of those things, he's your man. He has a bachelor's and master's in aerospace engineering and a PhD in engineering as well. And he's going to talk about big ship propulsions. And by big ships, we're talking about things that go to Mars and back, hopefully. So with that, I'll turn it over to Gary. Okay, so here's the microphone.
Okay. See if I can get that on there.
So this is for the slides. There's a laser.
Yeah. There we go. Yeah, there it is. Okay. My ranch, my front porch is 6 miles over to the test stand where SpaceX fires those engines. So I get to hear and see a lot of fire and smoke and noise. So yeah. And they are, I've heard a lot of those Raptor 2 tests. They light those in a pretty high power setting. The start is almost explosive. It sounds like something went wrong, but then you hear the continuing rumble. So they're lighting them at a high power setting. That's at variance with what most people have done since von Braun in World War II. That's already been covered right there. Where's my talking notes here? Yeah. Here we go. Let's see here. If I can find that laser pointer. There it is. Yeah, my first job out of college was at what was then Rocketdyne became Hercules in McGregor, Texas, where SpaceX is now and Beale Aerospace used to be. We made missiles out there. If you know what a harm is, or a Sidewinder, or a Sparrow Shrike, or any of those, that's what we made out there. I did spend a little bit of time doing aircraft and ICBM decoys at Tracor Aerospace in Austin. And I've been involved in all kinds of testing for most of my aerospace career, which came to an end when they closed the plant and put me on the market with almost 2 million other aerospace engineers when the industry was consolidating. So I had to go do something different. I did a little civilian engineering in these areas here, did a lot of teaching, taught at Minnesota State, taught at Baylor, taught public school. Yeah, I've done a lot of things. Kind of retired out on the ranch now, and accidentally invented a tool that will kill prickly pear cactus without all that grubbing and nasty hauling and picking up. All you have to do is drive around on a tractor and drink beer. That's is all you have to do.
What could go wrong?
What could go wrong? Yeah. Carry a shotgun because the rattlesnakes live under the cactus. The problem, what I got involved with. Now, Brian there knows about this because he and I and another fella that you heard last month have been playing with this notion of how do we send a whole lot of people to Mars at once? And it's going to take a great big vehicle to house up to 1,000 people and keep them alive for months in space and in comfort enough so that they don't go crazy, get them to Mars, and then get that ship back to Earth so it can make another run. So this, we're talking about reusable many times. We're talking about very large. We kind of approach this from the standpoint of that habitat is a deadhead payload. And then I got into this trying to figure out what kind of a propulsion stage can I put on this thing that'll push it all the way there. And we'll do that as a separable stage so you can add on better propulsion later. Now we're talking large scale here. I used an arbitrary figure. My deadhead payload number is just 5,000 metric tons, period, end of issue. If I could push something like that, I could probably push whatever they come up with for a habitat. So that's where we are. Now, I want to do this from low Earth orbit, and I want to do it in low Mars orbit. This is an orbit-to-orbit transport, and you want it in low circular orbit because your ferries coming from the surface can have pretty good payload to get to that orbit. If you put that in a higher energy orbit or an elongated orbit, you're talking about periapsis speeds that are pretty close to escape. That's a much more difficult thing to reach, and you're not going to be able to carry as much payload. So you want to base at a low orbit. Let's see here. Now, this is where it gets interesting. I didn't use computer modeling for this. I used the rocket equation. I used the same thing I did when I started out in industry, pencil and paper analysis with equations, assisted by a slide rule, later a calculator. Later on, many years later, we got desktop computers. That's what I used for this. I just automated the old pencil and paper calculations in a spreadsheet. Makes it a whole lot easier. Now, the rocket equation, I think everybody here knows what that is. That's right there. Okay, you need a mass ratio, you need an exhaust velocity, and that'll tell you what kind of delta V velocity change you can get out of that vehicle. That's the maximum. Okay, now there's two things involved here. You're going to need the right weight statement in order to get the right mass ratio to put in there. And you can turn from what they always report for the rocket engines, which is ISP, and you can turn that into an effective exhaust velocity. You know, it's just a little equation. That's no big deal. All right, now that'll deliver something. Over on the other side of the house over here, you got your orbit calculations that tell you what all these velocity changes need to be. Okay. And there may be gravity and drag losses involved with that. And if there are, you need to factor these up larger so that they cover the losses that these things are going to cause you. So you got to take these orbital calculations, and you may or may not have to factor them up depending on exactly what you're doing. And that's your required delta V. And what you deliver over here needs to at least be equal to that, or maybe a smidge bigger, so that you don't run out of gas on the way there. Now, if you're doing very, very simple calculations, which is what most people do when they play with this equation, you can take that number right there and you can work backwards. Find out how big it is that way, what your mass ratio has got to be. For real simple single stage burn calculations, you can work that thing in reverse like that. But if you're doing multiple burns, or your vehicle changes its weight statement because something got offloaded or something got added between burns, you can't do that. It becomes iterative. And that's where the spreadsheet come in. That helped. So this is what I was talking about, what I did. I played with this. This is their deadhead payload. And I'm sticking a propulsion stage on this thing. And I'm characterizing that propulsion stage with two numbers. One is the propellant mass fraction of that stage only, which also tells you what the inert value is of that stage only. If I've got a 100-ton stage and I have a 97% propellant fraction, I've got 97 tons propellant and I've got 3 tons of inert. Okay? To get from the stage only thing there, I need one number here to characterize that, and that's just the deadhead mass I have to push. That's all I need for these kinds of simple screening calculations. Okay, and I take that stage as inert and I add it to that deadhead mass right there, and that's the vehicle burnout mass. Then you add the propellant mass in here to that same burnout number, and you've got the ignition mass, and that's the mass ratio you can achieve. It's that simple. Okay, that's the way I did this. Whoops, I think I did that wrong. Yeah, there we go. Now, if you're playing with this, and I got into this pretty deep because it happened to me, if you're changing your, keep hitting the wrong button there. There we go. If you're doing multiple burns from the one weight statement, you're going to burn it. Yeah, you're not going to change anything. Your ignition mass and your burnout mass are the same numbers, but I'm going to do 3 or 4 burns before I burn it all out. All you have to do is add those delta V's up, and the mass ratios for those individual burns simply multiply together. But if you're changing that weight statement, let's keep hitting the wrong button. I'm sorry. You got to do a separate rocket equation calculation for each burn if you change the weight statement. And I had to do that for the space tugs I was using in some of these options to get that big ship out of orbit and onto the interplanetary trajectory, because that's a big delta V. And if you use a space tug, you can cut that way down for the big ship at the expense of using a big space tug stage. The trick there is if you don't throw that space tug away, you keep it in an orbit about the Earth where you can recover it easy. That's how you make it reusable. All right, now, launch versus on orbit. I can use the rocket equation all day long, and I can tell you I need X many tons to fuel this, and I need X many tons in orbit to fuel that, and X many tons in orbit to fuel that. Well, how am I going to get all that up there? I need a ferry. And that ferry is going to burn more propellant. It's going to burn a lot of propellant, putting what I need for this big ship on orbit. Now, there aren't any ferries yet. We looked at that in the previous presentation. There's only one big rocket flying. That would be Falcon Heavy. And it only carries, what, about 60 tons to low Earth orbit? I think that's what the number is. That's about all we got. We got SpaceX and their Starship Super Heavy is not flying yet. Starship has sort of kind of flown a little bit, not very far, not very high. They're still hung up with that permit thing down there at Boca Chica before they can try to make orbit. But that's something that carries more than 100 tons My numbers say about 170 tons to low Earth orbit eastward. Not the ISS orbit. That's a little more challenging. Just an ordinary low eastward orbit to about 300 kilometers. Well, that's this one here. Starship, at least the numbers I was using from a couple of years ago, SpaceX said that the propellant capacity, they used to report that on their website, would be about 1,200 metric tons of liquid oxygen, liquid methane propellants. Their super heavy first stage, at that time, they were saying would hold about 3,400 metric tons of that same propellant, using the same engines, just more of them. And my calculations, flying this thing with my rocket equation calculations, approximation, they said more than 100 tons to orbit. That's all they ever claimed so far, but I was getting numbers somewhere close to that 170 tons right there. That's what I used for this study. And I just said, that's an Earth ferry. Anything we do in the future is going to look about like that. It's going to carry payloads that large, or it's not going to be practical at all. That same ship, I looked at it, just the Starship second stage can be operated with a high payload, single stage to orbit and back at Mars because the gravity well is weaker. You don't need a two-stage rocket. It only takes one. And it'd carry, my numbers were pretty fuzzy, so I just kind of rounded that off to about 200 tons. It's a guess. It's as good a guess as any at this point. So you're going to use 1,200 tons of propellant to put 200 tons of propellant on orbit if you use that thing as a tanker at Mars. If it's less dense than LOX methane, you're going to need a bigger payload compartment. That's going to affect the inert weight a little bit. The numbers might change. That's okay. We're looking for trends here. That's 6 tons of propellant per ton of payload that you can launch on Mars to low eastward orbit. Over here, 171 tons takes 4,600 metric tons of propellant to fling that to orbit. That's about 3%. 26.9 to 1 is the ratio that I was using for my studies. Earth's got a heavier gravity well. You got to work harder to fling it up there. That's not surprising at all. And in fact, that ratio is pretty well in line with the launchers we've been using all these decades. I'm getting the same numbers we've always gotten. Okay. Now, using chemical propulsion to push this great big thing to Mars without any space tugs or anything, I'm just going from low 300 kilometer eastward orbit about the Earth to low 300 kilometer circular orbit about Mars. And here's the delta V's right here. That's pretty substantial right there, 3.8 kilometers a second. That's pretty substantial. Not so bad at Mars. These are for average planetary positions. When Mars and Earth are at their farthest from the sun, these numbers get larger. That one right there gets close to 4. This one here gets a little above 2. When it's at perihelions, the numbers get a little bit smaller. These average planetary distances would be more or less representative of what you'd find most of the time, because the planets won't be at those peak distances or min distances most of the time. They'll be somewhere in between. So I just use the averages. What ballpark are we playing in here? All right, now this thing, it has to make a burn there to get onto the trajectory. I threw in a little kitty for course corrections. And then it's got to make this burn here to get into Mars orbit. And then it's got to make that burn again to get onto the trajectory home. And another kitty for course corrections. And it's got to make that burn again right there to get back into Earth orbit where it can be refitted and reused and sent on another mission. Now I used the Hohmann min energy transfer for this. That's about a 30-month mission. The planets line up to make a trip every 26 months. So you can't go every time they line up. You can go every other time they line up. So I got 52 months between flights to make all this propellant that I need to send up there if I'm going to do it this way. All right. If you look at that number right up there, this is an awfully big propulsion stage. It's got almost 1/3 of a million tons of LOX methane propellant on board to make that round trip. That is a monstrous stage. That's going to be expensive, guys. I'm not sure we want to do it that way. All right. This is scaling that number up to what it takes to make the propellant required to launch it. How much you're going to have to make in total. Here's that. I went ahead and divided by the 171 metric tons per tanker flight to get about 1,854 tanker flights to fuel this thing up. That's a bunch. That means I've got to make about 8.5 million tons of launch propellant. And when I add those two together, I've got almost 9 million tons of propellant I got to make per mission. This is not sounding so good, is it? I didn't think so either. And if I have 52 months to make all that stuff, I've got to be making propellant at almost 200,000 tons a month. Now we got the infrastructure. We could do that if we wanted to, but we're going to pay a pretty penny for it. We could do it. We could. I don't think the political will is there to do a thing like this, but that's what it would take if you're going to do it this way. All right, let's see here. Now, here's the Earth tug idea. See that elliptical orbit right there around the Earth? I picked an apogee distance from the center of the Earth about not quite 150,000 kilometers, where the pull of the Earth was about 3 times the pull of the sun upon that same vehicle at that distance. I figured that would be stable. That was just a guess on my part, but some other people have told me that I'm in the ballpark. All right. Now, here's that 3.843 kilometers a second I got to have to get onto that interplanetary trajectory. And this is not that 6-month thing. This is that home and min energy transfer. That's 8.6 months long one way. All right. Now look at here. This right here is almost 2.8 kilometers a second is the periapsis speed of that elliptical orbit. So if I'm in that elliptical orbit, when I get close to the Earth, to periapsis, hit the wrong one again. There we go. All I need is a little over 1 kilometer a second to get from there onto the home and min energy transfer to Mars. That makes my stage a whole lot smaller right there. Now, this one, keep hitting the wrong button. Here, I'm not doing anything at Mars like that. So I still have to make the 1.75 kilometers a second to get into low Mars orbit. This one's a lot smaller. Let's see if I can get my pointer again. Departure propellant is about 40,000 metric tons. That's a whole lot better for the big ship than that 300,000 metric tons of propellant, isn't it? Made a big difference.
Could you repeat that, please?
It's about 40,000 tons instead of 317,000 tons. Yeah, made a big difference. But I got a space tug that's almost as big as that other stage. All right, now let's look at another option. Well, here's what it takes to do that. Here's my Earth tug's got about 50,000 tons. The big ship's got about 22,000 tons for the round trip. I've got to fling something over 70,000 metric tons into orbit, and using that same 26.9 to 1, you get about the same number here. It's just over 2 million tons. That's better than 9. Made a difference. The nuances of how you run these missions can make a big difference. And I don't care what kind of propulsion you're talking about, it can still make a big difference. Not just chemical, it's all of them. Now, I'm not making any propellant at Mars. The only propellant you'd have to make there is for whatever you're using for a ferry at Mars to get from the surface up to low orbit and back down. You're going to be going up there to take propellant up to refuel it if you're using the tug there. This particular scenario doesn't do that. You're just taking people and cargo down, but you're going to have to make propellant on Mars to run that ferry. It's going to be based on Mars. You're not sending that from Earth. Now, chemical one way. Now, if I go one way instead of two way round trip, if I refuel that big spaceship at Mars with those same ferries, it makes another big difference. We're down to, I can't even read my own chart now. Here we go. We'll get the numbers later. Here it is. Here it is. We're down, instead of 40,000 tons, we're down to 21,000 tons. All right, let's see. Here's one with tugs at both planets. Now I'm going to fly the big ship one way, which means I'm going to refuel it at Mars, and I've got to refuel my tugs at Mars too. But now my big ship needs 3,000 tons, 3,300 tons to make the one-way trip to Mars. I need about not quite 12,000 tons for the Earth tug that flings it out into that elliptical orbit. All right. And then I need a little bit of arrival tug here to catch him. I'm gonna capture at Mars in that same elliptical orbit at Mars. It's about 75,000 kilometers apoapsis altitude at Mars. But and then use a tug there to bring him from there to circular, so that I don't penalize the big ship for these delta V's between the elliptical and the circular. That's what the tugs do. That's how I'm getting away with making the big ship smaller. So I've got some numbers here for that. But rather than belabor it, we'll go on through it because I'm going to show you the comparison with all of these here in a little bit. Here's one way with nothing but an Earth tug. If you look at this chart in detail, I've got the big ship, I've got the Earth tug, I need, and I've also got to catch the big ship when it comes back to Earth. So I'm going to need about 30,000 tons in Earth orbit. And then here, I've only got the big ship to refuel at Mars. I don't have a tug. So this will reduce the propellant requirement at Mars, but it makes it a little bit bigger at Earth. That's what's going on with this. These nuances really do have serious effect. Now here's one way of doing a tug at Mars only. This one didn't turn out very favorable. I've got to make an awful lot of propellant at Mars. There's 24,000 tons there that I need. And I only need about 13,000 tons at Earth. Well, it's easier to launch propellant at Mars. That might not be so bad, but there's no manufacturing infrastructure in place on the planet to do quantities like that. And there's not going to be for a while yet. So if we're talking about doing this a decade from now, this is going to be hard to do. If we're talking about doing this 30 years from now, maybe not so much. I don't know. I don't know when they're going to try to do this. But if they do, this is what we're facing. Okay? We got to solve these problems in order to do this. All right. Now here, the first study I ran, I looked at the big ship with no tugs, and I went one way, refueling at Mars. And this is the propellant I need at Mars. Let's see if I can get my chart here. I did it as a bar graph so you could kind of see what was going on here. I've got a big propellant requirement at Mars. I got a pretty big propellant requirement at Earth, or at least it looks like that until you realize what the top of scale is. Top of scale here is 200,000 tons. That's that mark right up there. Top of scale here for Earth is 900,000 tons. So the scales are different in the two plots. But the shapes are telling you what you want to do. Here I've got a bigger Mars requirement. Here I have a small Mars requirement. It's a little bit bigger here, but still small. And then it goes way back up here. Now this is the baseline, no tugs. It's a one-way ship. This is an Earth tug only. This is tugs at both planets. And this is a Mars tug only. Now look at the propellant at Earth. Here's the big ship. This bar and this bar and this bar are all about the same height. This one, hey, we're going to have more. This is the Earth tug only. You've got, this one is acceptable with a small Mars requirement here. That's using tugs at both planets. So if you're going to try to do a thing like this, especially with this kind of propulsion, if you decide to take on quantities like this, that's the way to do it. It's that simple. And the relative heights of those bars tell you the story. Now on the right, these are the quantities, the rates. That's these numbers divided by 52 months. Now for the quantities, top of scale, right here for Mars is 60,000 tons, I believe. And for Earth, it's I'm sorry. It's 1,000. No, I'm not reading this right. Something's wrong here. Oh, I'm looking at the wrong one. No wonder. 3,500 tons a month is top of scale at Mars, and 18,000 tons a month is top of scale for the rates that you need at Earth. All right, so we're talking about needing to make about 3,300 tons of propellant a month on the surface of Mars to support this operation. That's a lot. That's a lot. Consider the fact that SpaceX thinks, or at least a couple of years ago, they thought that it might take about a year to refuel one Starship for the return flight to Earth, and it holds 1,200 tons. So you're talking about making 100 tons a month come dust storms or not. That's where they were thinking, just to fly one ship back. All right, if you're gonna fly two back, you got to double that. We're talking about quite a bit more here. That's about 3,300 tons a month. It's going to take some infrastructure on Mars to support an operation like this, especially if you're going to use this kind of propulsion. All right, now let's see here. I looked at NERVA. Remembering what the numbers were when I first entered the workforce decades ago. And I used a little bit lower stage propellant fraction, 95 instead of 97%. And I'm using 800 seconds of specific impulse, which is about what they demonstrated in the ground tests. This thing was ready to go on its first experimental flight test when the program got canceled in 1974. This was one of the propulsion modes they were looking at for what was then planned to be the 1980s manned Mars mission. All of that got canceled in 1972 with the restriction of all manned flight to Earth orbit. And NASA canceled the nuclear rocket because who needs the rocket if we're not going to go? So that's why that technology got left behind. I flew this thing 2 ways unrefueled. That's a total delta V required of the single propulsion stage of almost 12 kilometers a second. And the weight statement here, I've got the deadhead, I've got about 1,000 tons of stage inert, burnout weight's about 6,000 tons. I've got about almost 21,000 tons of propellant on board. And that's to fly it 2-way, not 1-way. I'm flying the chemical propulsion 1-way and I'm talking 20,000, 21,000 tons. This is 2-way, this is round trip, unrefueled. Unrefueled round trip, 20,000 tons. It's still enormous. 21,000 tons of liquid hydrogen I have to deliver on orbit at Earth. Okay. This is what the NERVA looks like if you do it 1-way and say, I'm going to make liquid hydrogen on Mars and ship it up at Mars. Let's see. I'm down to 11,000 tons loaded in the stage, but I got to do that at Earth and I got to do that at Mars. Okay, it's not so bad. These numbers are getting smaller. That's the higher ISP. Okay, nothing, no mystery there. Now here's one way with an Earth tug. I'm going to use a NERVA stage as a tug to push my NERVA stage equipped big ship to Mars. And then when it comes back from Mars, I want to capture into the elliptical orbit and go get it with that same tug and bring it back to low circular. All right, let's see here. Weight statement, one way refilled at Mars. Here we go. Here's the Earth tug there. We got about not quite 200 tons of inert, and it holds 3,700 tons for Earth departure. Only needs about 2,600 tons for the arrival because the big ship is lighter. It's depleted of propellant. Big ship. Where's the big ship numbers go? Here we go. About 126 inert tons that get added to the 5,000. And I need just under 2,400 metric tons of propellant. Hey, if you operate it like that with the Earth tug, it looks even better than it does with just flying it from circular orbit to circular orbit, doesn't it? The numbers are coming down. These nuances are important. All right, now here's one-way tugs. I got tugs at both ends. Rather than belabor this point, I think I'll show you the comparison bars in the chart coming on, but the numbers are dropping. We're down to 3,000 tons here for the Earth tug, 3,000 tons of propellant. I've got about 1,200 tons in the Mars tug, and the big ship has about not quite 1,400 tons. It's starting to look a little more reasonable, isn't it? This space tug thing, this works. Here's one way with a Mars tug, and once again, that didn't turn out to be as favorable. Things got a little bit bigger, so we'll just kind of skip over that a little bit. And here's all the studies with NERVA. Here's NERVA flown single stage 2 ways. That's how much propellant I need at Earth. I don't need any propellant at all at Mars. There's nothing there. Now here is the new baseline. This is NERVA flown 1 way refilled at Mars, but I'm not using any tugs. Okay. This is what I need at Earth. All these bars, they're all in about the same ballpark. All right. Propellants at Mars, I need a lot of propellant at Mars. Now, if I go the first variation here, here's NERVA with a tug at Earth and at Mars. I'm on this bar. This one here is a tug only at Earth. And you see it's a little higher because I've got to work a little harder. All right, now here's over at Mars. Here's this one here is just refilling it in circular orbit at Mars. Here is using Earth and Mars tugs, and here is using only an Earth tug. It reduces the Mars requirement. Okay, then if I use a Mars tug, I can reduce the Earth propellant requirement, but it jacks the Mars propellant requirement way up. Now let's see, this is chart 21. Let me tell you what the top of scale is. Top of scale quantity at Mars here is 60,000 tons per mission. And at Earth, it's 700,000 tons. That includes the launch propellants, guys. The 26-to-1 at Earth and 6-to-1 at Mars. All right, it makes a big difference. You get bigger numbers when you look at what it takes to fling it all up there. All right, now here's the rates over here. If I fly the thing single stage 2 ways, round trip, man, I got to have a big manufacturing rate. These others don't look so bad over here. Now, here's the one that really looks good for not having so much Mars infrastructure to make propellant. Now, top of scale right there on the manufacturing rates, let's see, is 1,000 tons a month. Now, that's about 10 times what they're anticipating they need to fly a single Starship back from Mars, but it's only 10 times. It's not those monstrous numbers that I had earlier. It is liquid hydrogen. I got to get liquid hydrogen into low Mars orbit to fuel up this NERVA. That's what it burns, it's liquid hydrogen. All right, so it's important, even for NERVA, to do the space tug thing. That's the message here. Now I looked at a nuclear light bulb. Now the numbers that I'm going to show you for things like this are very speculative, and I got an awful lot of them out of the proposals written by Maxwell Hunter and Pratt & Whitney United Aircraft back in the 60s and 70s. And it was speculative. There's some reason to think that the nuclear light bulb might actually work if we decide to build one. They did enough experimental work to figure out that we really could do this, but there's still a lot of problems to solve. The thing about the nuclear light bulb is you've got liquid hydrogen propellant separated from a gas core uranium fission reaction by some kind of double quartz wall that's cooled with some of that liquid hydrogen. You're not putting radioactives into the exhaust. They thought they could get about 1,300 seconds of ISP out of that back then. I don't know what the thinking is today. Doesn't matter. Let's find out what ballpark we're playing in. Go ahead and use Maxwell Hunter's numbers. Now I flew the thing 2 ways, and I found out I could really do it. Round trip, fueled only at Earth, round trip to Mars, pushing that 5,000 ton deadhead payload atom. And I need about 8,000 tons of propellant to do that on orbit. Well, not so bad. That's the effect of the ISP for the advanced propulsion. All right. I looked at gas core regenerative cooling. It's another one of Maxwell Hunter's proposal ideas. The best numbers they had on paper calculations back then said that you might get 2,000, 2,500 seconds of ISP out of that, but you've got a limit on how high a reactor power you can run because regenerative cooling is no longer enough if you go above that. You got to do something else. Here, if you limit it to 2,500 seconds, which I did, this is a 2-way round trip, circular to circular, no tugs, no nothing. This is about 3,000 tons of propellant. That's the higher ISP in action right there. Okay. Then I looked at the thing that NASA was looking at for the advanced nuclear version of the 1980s Mars mission. That's the gas core reactor operated at full power with giant waste heat radiators to cool the engine, keep the thing from melting down. And I knocked the propellant mass fraction way down to account for those radiators. But you're looking at 6,000 seconds of specific impulse for this. That's what NASA was looking at about 1970, 72, somewhere in that range. That's what they were looking at for this.
So an ISP is 6,000.
6,000 seconds, yes, sir. That's what they were looking at. Some people said it might go as high as 10 or maybe even 12,000, but they were trying to be conservative in those days. That's all I used, okay? Once again, flying this thing round trip, unrefueled, you're down to 1,180 tons of propellant that you need on orbit. All right, that's starting to look at this ISP thing. This is important. And the fission explosion drive, old Air Force Project Orion from 1959 to about 1965, done at General Atomics in San Diego. Flown the same way, 10,000 seconds of specific impulse, 640 metric tons of those fission devices popping out behind that pusher plate at 1 per second. They're about 3-4 kilotons. That's the old firecracker under the can technique. That's what that is. It's real hard to hold the ship acceleration down to 4 Gs when you do that. This is a high thrust, high impulse propulsion mode. It flew as a 1 meter scale model with high explosives under its butt. Air Force didn't want them to do that, but they did it anyway, and it flew. And the survival of the pusher plate is based on some of the large steel structures that were present at the atomic tests in Nevada in the 1950s. It will survive. We have a pretty good idea that if we did this, it would work. there's a lot of problems to solve, not the least of which is electromagnetic pulse, which they didn't know about in the 1950s. That showed up with the Starfish Prime shot in 1962 when it knocked part of the grid down on Oahu from a nuclear explosion, 2 megaton nuclear explosion, 200 miles up at Johnston Island, 900 miles away. Knocked part of the grid, part of the phone system down. And I'm talking about 1962 vintage grid, 1962 vintage phone. That stuff, by today's standards, that's old electromechanical stuff. It's almost nuclear hard. Operating this thing in low Earth orbit could be a problem. But I ran the numbers anyway. All right, and I looked at an electric drive. I just put some generic numbers up there. I used 3,000 seconds of ISP, and I assumed that either my nuclear power plant or my solar panels weren't all that heavy. I used probably too high and it stage inert fraction. That's not too bad. Flown unrefueled two-way, that's not quite 7,000 tons of whatever argon or xenon or whatever that thing uses. I got to deliver that, a few thousand tons of that per mission to orbit. That's not too bad. Then I looked at another study. I took that gas core, that 6,000 second gas core, and I looked at what you might do if you flew a fast mission instead of home and transfer. The fast mission I looked at, here's the home and the ellipse between Earth and Mars. That's the sun right there in the middle. Here's Earth, here's Mars. On the fast mission, if I pick the period of that orbit to be 2 Earth years, then if you abort, you just fly around the orbit, Earth will be there when you get there. That's an abort orbit. It has to be an integer multiple of Earth's period. It'd be an integer multiple number of years. Otherwise, it won't work as an abort orbit. I just picked that one. My numbers say it takes about 4, not quite 5 months to get to Mars right there. You've got a big delta V because you got a big angle change. And then you got about a year before this point happens and you can come back. It's the same 2-year mission to do that as it is to fly all the way around there like that. You got about a year at Mars. So I looked at the gas core again, looked at it two-way, unrefueled. I looked at it and I looked at it on the fast mission just to see what that would do to it. Now here's what it looks like. This is what the gas core study looked like. Here's the two-way stuff. This is metric tons of propellant at Earth. That's this one. And here's metric tons of propellant needed at Mars. Now if I fly two-way unrefueled, I don't need propellant at Mars here or here. If I fly one way and refuel it at Mars, I need some propellant at Mars that I got to ship up. Now that little bit right there, that's the hydrogen for the gas core engine. The rest of this is the launch propellant. Okay, I'm assuming the same chemical propellant, the same transports, the same ferries, because you don't want any of that nuclear stuff all over your launch pad if you're going to reuse things. And those open cycle gas cores, there's some hard radiation in that exhaust. You really don't want to fire that down here. Okay, I mean, you won't want to fire it at your spaceport on Mars either, not if people are going to live there. So I used chemical propulsion for my ferries. All right, now if I fly it one way, let's get a sense of scale here. This is the Hohmann transfer. This is the fast trip transfer. It cost me a little more because the delta V's are higher. Okay. The top of scale right there. This is chart 28. Let me get the numbers for you, because you can't read this stuff. I can't hardly read it just standing here. Top of scale quantity at Mars. Oh, hit the wrong button again. There we go. Here's at Mars. Top of scale right there. 7,000 metric tons per mission. That's including the launch propellant. All right, so we're talking about not just less than that, but if you fly a Hohmann min energy, the longer mission, it's quite a bit less. Okay, that's at 6,000 seconds of ISP. The nuances are becoming a little less important. All right, now here's the rates over here. These numbers divided by the appropriate interval are the rates. Now, with Holman, it's 52 months. You can fly every other mission because the mission itself is 30 months long. And planets line up every 26. If you fly that other mission, you can go every time the planets line up. You can go every 26 months, and that's why these rates are so much higher than they ought to be, because everything's up by a factor of 2. I can fly twice as often. Okay, it's still reasonable. It's not too bad. The propellant rates at Earth and Mars are, let's see, this is 300 tons a month at Mars. This is 3,000 tons a month at Earth. That's starting to sound reasonable. Starting to sound reasonable. Now here's a pattern. There's a pattern to this. And back in the old days, doing this with a calculator or a slide rule, you're not going to run these numbers enough times to see this pattern. Instead of iteratively determining the exact amount of propellant and inert weight that's going to go for my vehicle weight statement, what if I just plot the curve? I'm just going to assume as the propellant increases, so does the inert weight, so does and the mass ratio goes up, but you get to a point where they knee over. That's the upper limit to what you can do. If you're on this part of the curve, a small change in added propellant gets you a big change in mass ratio. This is mass ratio on the vertical scale, and this is the propellant added in the stage. How much propellant is in that tank right there? That's what I'm looking at. Now, here, this is what you can do with a stage propellant mass fraction of 97%. If it's 95, you top out lower. If it's 75, you top out lower, or 90, you top out lower still. If it's 75, you top out lower still. And if it's 50%, you top out lower still. Now, those low stage propellant mass fractions are high stage inert mass fractions. If you're carrying a nuclear power plant or a giant set of radiators or equipment like that, your stage inert fraction is going to be high. It's inevitable. It's going to happen. Okay, now that's mass ratio. You take the log of that mass ratio and you multiply it by the effective exhaust velocity of the rocket propulsion that you're looking at, and that's where ISP gets into it, because that's just a units conversion factor times your ISP. It knees over too. It's got the same shaped curves. And this is chemical right here. All right. This right here is what you can get at 97% stage propellant fraction with LOX liquid methane. You're right on the hairy edge, and this right there is what you have if you're going to go two-way, no tugs, round trip unrefueled from Earth. It's right on the hairy edge of what might possibly be feasible with chemical propulsion. That doesn't mean it's economically attractive. We've already seen the enormous numbers that you get for propellant quantities. There's a difference between technical feasibility and practical or economic feasibility. Where you really want to be is not only left of the knee in the curve, because see on the right of the knee, you take an enormous change in the size of the propellant you need, and you get almost no benefit at all. You got to be left of the knee. You really want to be down here close to the origin, where the propellant quantities are smaller, and you can afford them, and this starts to look attractive. That's what you get when you just plot the curves and superpose on them. This is what I need if I'm going to fly it without tugs. This is what I need if I'm going to fly it without tugs. And I am going to refuel at Mars. I'm only going to make the one-way trip, refuel and make the one-way trip back. See what an enormous difference that made? The mission nuances are critically important, especially at low ISP. I'm using 380 seconds for this. All right. Now, here's what some of the tugs did to it. I've got this other chart over here. This one here is that same baseline two-way mission. This here is that same ship alone refueled at Mars. Here is the big ship with tugs. That's 4. That's Earth tug only. 3 is tugs at both, and 5 there is tugs at both. See how these space tug nuances get you down close to the origin, even with chemical propulsion. It's possible to do this if you're willing to pay the price. That price down there with the space tugs is a whole lot better than that price way up there, the way we used to think about it back in the 1950s when people were just starting to dream about going there. Okay? So these mission nuances are really, really important to the way the rocket equation works out. Now remember, I've got lots of significant figures in these numbers that are not justified. This is really 3 significant figure stuff. That's all this is. But it tells you what the trends are, and you find out what ballpark you're playing in. You can make an intelligent decision about where to concentrate the effort of building real computer models that get you good data. It takes time to do that. And those models are kind of limited in how many variations you can play with. So before you expend all that effort, this kind of study helps you find out where you ought to concentrate it. This is what I used to do. I was infamous for this. Let's see here. This is the pattern with NERVA. 800 seconds. It's the same mass ratios because ISP doesn't figure into the mass ratio curve. But over here on the delta V curve, looky here. Here's two-way unrefilled. Here's one-way refilled only at Mars, but no tugs. Look at there. It made a huge difference, but we're already down closer to the origin. That's why those numbers were more favorable. Here's the pattern with the nuclear light bulb. Again, same mass ratios, but it's a higher ISP, so the delta V's are higher. Here we are, way down here close to the origin, a two-way, no tugs. And if you refill at Mars, it's even lower. It still makes a difference. It's just not the astounding difference it made with NERVA and with chemical propulsion, because you're already down close to the origin. That's the effect of the high ISP. Tells you what ballpark of ISP you need to be playing in. You need to be doing about as good as nuclear light bulb or better. Gas core regenerative. Once again, here we are unrefilled. Two-way trip, round trip, unrefilled. We're already down there as good as any of the things we've seen so far. Here we are with the 6,000 second gas core that had to have the radiators. You're down here. Here you are with the explosion drive. You're down here, unrefilled. What would be the point of doing space tugs with that? You're already down about as low as you're going to go. And here's the generic electric. It's a little higher because it's only 3,000 seconds, but you're still down here. Now, you're not going to use electric propulsion for any space tugs with that because that's a very low acceleration, low thrust type of propulsion. But you could do it from low circular orbit about the Earth, spiral out. It's going to take about 3 months, spiral out through the Van Allen belts. Then you're going to spiral out from the sun about halfway and then start spiraling on a slightly different slope as you slow down, as you approach Mars, and then it'll take you about a month to spiral into low Mars orbit. Now, while you're spiraling out through the Van Allen belts, you're going to need radiation protection of the type that would protect you from a major solar flare event. It's similar radiation. You can stand a direct hit from a Class X flare. You can stand the Van Allen belts. Now, the big ship that Robert Dyke was talking about last month and that Brian here's also been working on, and I've been trying to help him a little bit with that. We're talking about a thing that spins for artificial gravity and has radiation protection built in. If you're going to spend months in space, you need the radiation protection because it's almost inevitable. The longer you spend out there, it becomes inevitable that sooner or later you're going to get hit with a flare. There was one in 1972 between two of the Apollo missions to the moon that would have killed the crew had they been out there on a mission at that time. You're talking about the same kind of radiation exposure rates that you would have if there was an atom bomb blew up 5 miles over there and I walked out that door into the fallout. I'd be dead in an hour, and it's an ugly death. You're going to need the radiation protection if you're going to fly out there for months at a time. The only reason that we survived Apollo was those missions were less than 2 weeks long. The odds were good. They were just betting that it wouldn't happen. That's an issue that is going to have to be addressed. For space colonies, it's going to have to be addressed. For travel to the other planets, it's an issue along with microgravity that's going to have to be addressed. The way we've been doing it is not the way we're going to do it in the future, because we're going to hurt somebody doing that. All right, generic electric, it worked. Here's the overall results. Now this includes, if I can get there's my pointer. Let me see if I can find top of scale again here. Here's my notes. What I'm looking at here is the total propellant requirements on orbit, plus all the launch propellant that you got to have to fling it up there. That's what this bar chart is. And there's all the studies that I ran. Across here, they're listed here. It took me 2 columns to get it all written down, everything that I ran. This is chemical, 2-way round trip, no tugs. And you're looking at, let's see, the top of scale on that chart. Let's see, chart 36. This is the, oh, damn, keep hitting the wrong button. This is the Earth, yeah. This is the blue column is the Earth propellant. There's these little bitty things here that you can't even see in this light in here. That's the Mars propellant. It doesn't hardly show up at all. But 38, where's top of scale? 36, excuse me, I'm looking in the wrong place. Oh, here's top of scale, it's written right here. This is 30 million tons of propellant is the top of scale right there. So you're looking at nearly 30 million tons of propellant if you try to do it the old 1950 way. This is chemical flown 2-way with an Earth tug, cuts that down to 2 million. And then here's the chemical tug study. See the difference that made, how short those bars are right there compared to that one? Here's the NERVA study that I showed you. Here's the electric and the explosion drive. Here's the gas core study that I showed you. It doesn't even show up at this scale. So let's delete the high bars. These are the rates here. That's just these numbers divided by either 52 or 26 months as appropriate. Now here's 700,000 tons per mission. This one here is the chemical 1-way Earth and Mars tug. That's the best chemical mission right there. And we're up here at about 600,000 tons of total propellant per mission. And then we're down here, there's a little short bar. That's how much I got to make on Mars. All right. Number 2 here, here's the best NERVA. This is the one, the NERVA operating with an Earth tug only. That almost zeroed what I need at Mars. Almost. All right. Number 3 here, this is the generic electric. Now, the nice thing about electric is it's flying. That's out there in satellites now. It's in some of the probes we've sent out now. It just needs to be scaled up from pushing something about the size of one of these boxes to a 5,000-ton ship. We got to scale it up. We got to scale up the power plant or the solar panels or whatever it takes to run that stuff. down around, I can't believe I'm sorry, down around 2,000 to 3,000 tons a month. Do that. That's not that big a deal. All right, and y'all look at these are all flown without any component. Mars. That's an attractive point to look at. Feasible to do within a decade or so. 20 years from now, 25, maybe 30 years from now, however long it takes, if we can get the explosion drive or any of the gas force stuff running, it looks even better. Just change out the propulsion stage and keep shipping people. It's that simple. Now I did that with something. Here's the conclusions. This is what I drew from it. If you're going to use chemical at less than 500 seconds of ISP, you've got you're not going to like the price tag. All right, if you do this with 1974 vintage NERMA performance at 800 seconds, refill it Mars and do it only in Earth tug. That gets the Mars infrastructure requirement down, which is something you need to do. It's going to take us a while to get that infrastructure built. It takes time, just like it did here. All right, if you're going to fly hot, it's 1,300 seconds for nuclear light bulb or anything hotter than that. The nuances are less important. You can just go circular to circular if you want. It's not going to make much difference anymore. That's far enough down close to the origin on those trim plots. You can afford it. Okay? What's that big a deal? Now, the only thing flying among that advanced propulsion is the electric, so that's where you start. But what's warranted here is getting some intense development going on that gas core and explosion drive stuff, because that's where the future runs. Just like it did, it's like they thought it did in 1960. It really does lie there, and these numbers don't lie. These are the trends. I haven't seen anything different about what I got than what people have been getting all these decades. It's all the same. All right. Using that rocket equation, when I first entered the industry, everybody, me and everybody around me, that was our calculator. That's what you run numbers with for 300 years before there was such a thing as a pocket calculator. That's a slide rule. There's a few people in this room old enough to know what that is, but not many. When I went to work at the rocket plant, that's what we were using, all of us. The way I used that rocket equation, I didn't use that anymore. I used a spreadsheet so that I could create these plots that I just showed you, and I could do the iterations easily without having to do it again and again manually. It's the same kind of little screening calculation. It's real easy to do. I did so many studies, and I didn't spend all that many hours doing this. I really didn't. Okay? What that does is tell you where you need to spend your effort to set up your computer models to refine these numbers. That too. I know what that's like. I've done that. I've written programs myself. And some of this orbit stuff, I got my first taste of that when I first went. Oh, I was still a graduate student. I took the summer off and I worked at what was then LTD Aerospace up in Dallas on Scout satellite launcher program. And I played with trajectories and configurations and orbits, the very same thing I did here. I've got a history of doing this. These screening concepts, using this equation this way with these little hand calculations augmented with spreadsheet, they don't teach that in engineering schools anymore. They should, because this sets up what you need to spend your big efforts on. This is the screening tool that tells you what's worthwhile to chase. I think I already told you what that is. Get started with electric, and add that nuclear stuff later, and that's how you send people to Mars, 1,000 folks at a time. That's how it's going to be done. It has to be. Physics don't lie. All right, contact data questions. You may have questions? Yes.
Question. So the shape of the structure of the aircraft or the craft that goes to Mars, does that matter?
No, these ships fly from orbit to orbit. They're in vacuum all the time and they're not landing. These are spaceships designed only to fly in space. Once they're built up there, they stay there. You could use it for 100 years if you wanted to. Just putting better propulsion on it and keep using it. Yes, sir.
We had a lesser possibility that was 26 months during the if we're going twice as often, does it make sense to make the ship half the size? Or does it scale linearly?
At this level of analysis, it would scale linearly. It doesn't really, but as long as you're in the ballpark, you're going to get the same answer. Okay. It's good enough. These trends are good enough to point you in the right direction. They're not design numbers. You can't use this for estimating performance, but you can screen doing it this way versus doing it that way and figure out what ballpark to play in. Then use the computer to find out what the score of the game is. It takes some effort to use that computer. It doesn't take much effort at all to do what I do. So, yeah. Back that summer job I told you about, there was one of the things I did that summer was I came up with an advanced configuration for Scout, a 2-stage configuration instead of the 4-stage solid that it really was. It pushed a great big payload. And it was a chase mission. We launched 30 seconds after Minuteman 3, caught it in flight and kept that payload alongside as it left the atmosphere. Okay. I did that in the summer. About 2 years later, I saw that mission being flown as a photograph on the cover of Aviation Week magazine about 2 years after I did that. And about 6 years after that, I found out what the payload was really doing because we launched an ASAT under the wing of an F-15 and busted a satellite with it. They're trying to figure out what these things look like so that they can target them. So, yeah.
So,
Yes, sir.
question online. David was wondering, is there a reason that you didn't consider using ISR resources from the moon in some of your calculations?
We could do another study and see what effect that would have. This is by no means all the things that could be done. I just looked at. I don't know. I didn't look at that. With the other propulsion that's hotter, yeah, you got room for big 70 factors.
Yeah, and I would definitely design it if I would build it, yeah.
Use electric, yeah.
They don't go into orbit. They don't have the mass ratios to orbit Mars and carry payload at the same time. They're using aero braking to fill 99% of that energy, and then all they have to do is fill the land. But I think I've seen the simulations they had on their website. It's just my hunch here at old aeronautical guy. He's going to have to apply for us. He's talking about just an area. They're coming out of hypersonics to 5 to 15 below the surface. Pretty close. Talking about a Mach 2 pull up. I think they're going to have to apply for us.
The wireless mic, unfortunately, the battery died.
Oh, I thought I heard something.
So anyway, so I am broadcasting from my phone. So that's the story there.
Anything else? Well, I hope you found it entertaining.
Hey, Nathan, was my question asked? I don't know if the sound was off at that point.
Oh, well, thank you so much. I really appreciate you coming. And you came all the way from McGregor. It's like a 3.5 hour drive, I think. Well, so stick around and talk to. I will. That'd be great. Okay. Well, let me go ahead and put this. Well, I thank you all very much for joining us online. We're going to go ahead and sign off here. So take care. Thanks. Okay. Well, thank you all for joining us. Stick around to eat some dinner. One thing I should point out is